Welcome to our study of one of humanity's oldest and most intimate companions. Today, we are going to explore the fascinating, albeit slightly unsettling, world of the human louse. We will uncover how this tiny, wingless insect acts as a biological vector, carrying dangerous microscopic pathogens from person to person. By understanding its biology and the mathematics behind its spread, we can see exactly how massive historical plagues were born. Let us dive in. To begin our journey, we must first understand the basic nature of this parasite. The human louse is the ultimate hitchhiker. It is a tiny, wingless insect that relies entirely on human body heat and human blood to survive. Why does this matter? Because its survival is so tightly linked to our body temperature, it is highly sensitive to changes. If a human host gets too cold, such as after passing away, or too hot, like when suffering from a high fever, the louse immediately jumps ship to find a new, comfortable ride. When it jumps from a sick person to a healthy person, it carries dangerous microscopic pathogens with it, initiating the spread of disease. Now that we know how sensitive they are to temperature, let us look at their biological classification. Human lice are obligate ectoparasites. This means they live exclusively on the outside of the host and absolutely require human blood to survive. They belong to the insect order Siphunculata. In the context of human infestation, there are three distinct types we must be aware of: the head louse, the pubic louse, and the body louse. While all three of these parasites cause intense itching and severe discomfort for the host, they do not all play the same role in spreading plagues. We must distinguish between them to identify the true biological vector. While there are three types of lice, we must focus our attention on the most dangerous one, the body louse, known scientifically as Pediculus humanus humanus. This specific type acts as a major biological vector for human diseases. What makes the body louse unique is its evolutionary adaptation to clothing. Unlike head lice, the body louse lives and lays its eggs deep in the seams of clothing, only moving to the bare skin when it needs to take a blood meal. This specific behavior makes it highly transmissible in crowded, unhygienic conditions, such as refugee camps or trenches, where people simply cannot wash or change their clothes regularly. Understanding where the body louse lives naturally leads us to how it actually spreads disease. Unlike mosquitoes that inject pathogens directly into your bloodstream through their saliva, the body louse uses a much dirtier method. This is known as posterior station transmission. When an infected louse feeds on a human, it simultaneously excretes feces onto the skin. Because the louse bites are incredibly itchy, the human host instinctively scratches the bite site. This natural scratching action accidentally rubs the pathogen-laden louse feces directly into the open bite wound, or sometimes into the mucous membranes of the eyes and mouth. It is a mechanical transfer driven by the host's own reflexes. Let us visualize this crude but highly effective mechanism with a detailed diagram. On the screen, you are looking at a cross-section of human skin. Notice the body louse actively feeding, which creates the small bite wound labeled at the bottom. Crucially, look just behind the louse. You can see the infected feces being deposited directly onto the skin surface while it feeds. Because the bite is intensely itchy, the host reacts. Observe the human finger and the motion arrows indicating the scratching action. This scratching physically pushes the pathogen-laden feces into the open bite wound, marked as the pathogen entry point. This diagram perfectly illustrates why the disease transmission is not from the bite itself, but from the host accidentally rubbing the infectious waste into their own bloodstream. Now that we have seen the transmission mechanism, we must identify the specific threats it carries. Through this crude posterior station transmission, the body louse acts as the primary vector for 3 major bacterial diseases. The most devastating of these is epidemic typhus, which has historically wiped out entire armies and populations. The second is trench fever, notoriously common during the World Wars due to the horrific conditions in the trenches. Finally, there is louse-borne relapsing fever. All 3 of these diseases thrive in the exact same conditions that the body louse thrives in: overcrowding, poor sanitation, and the inability to maintain basic hygiene. Knowing the diseases they carry, we must now ask, how quickly can an infestation spread? Because lice reproduce continuously, as long as they have a host, their population grows exponentially. We model this using the standard exponential growth equation. N of t equals n naught times e raised to the power of r times t. Let us break down these symbols. N of t is the final population we want to find. N naught is the initial number of lice that start the infestation. The variable r is the daily growth rate, which depends on temperature and blood availability. The variable t is the time in days, and e is the mathematical constant. If the growth rate r increases, perhaps due to warm winter clothing, the final population will skyrocket much faster, drastically increasing the risk of disease transmission. Before we move on, let us see this exponential growth formula in action with a concrete example. Imagine a resident in a crowded shelter acquires a small initial infestation of just 5 lice. We are given a daily growth rate of 0.1, and we want to find the total population after 30 days. We chose the exponential model because lice reproduce continuously. First, we substitute our known values into the equation. Next, we simplify the exponent by multiplying 0.1 by 30, giving us 3. We then calculate the constant e raised to the power of 3, which is approximately 20.085. Finally, we multiply this growth factor by our initial population of 5. The final answer shows the population has grown to approximately 100 lice. Physically, this means a seemingly harmless contact quickly turns into a severe infestation, drastically increasing transmission risks. So, we have proven that louse populations explode rapidly. This brings us to the actual infection process. We must examine the mathematics of how vector density translates into human disease. It is important to understand that just because a person is bitten by an infected louse, it does not mean they will automatically contract the disease. There is a specific probability associated with each individual bite, which depends heavily on how much infected feces is actually rubbed into the wound. To find the overall risk to the human host, epidemiologists use a cumulative probability model. This model helps us understand exactly how the sheer number of lice directly increases the mathematical certainty of infection. To quantify this infection risk, we rely on a specific cumulative probability model. Just because a person is bitten does not mean they automatically get sick. The formula is P equals 1 minus the quantity 1 minus P raised to the power of n. Here, capital P is the total overall probability that the human host will contract the disease. Lowercase p represents the probability that a single infected louse successfully transmits the pathogen during one feeding. The variable n is the total number of infected lice on the host. The term inside the parentheses, 1 minus p, represents the chance of a single louse failing to transmit the disease. As the number of lice, N, increases, the failure term shrinks, and the overall probability of infection, capital P, rapidly approaches 1. This means that with enough lice, infection becomes almost mathematically certain. Now that we have our probability formula, let us apply it to a real-world medical scenario involving epidemic typhus. Suppose a healthcare worker is bitten by 4 infected lice, and the probability of a single louse transmitting the bacteria is 30%, or 0.3. We want to find the total probability of infection. We use the cumulative probability formula to account for multiple independent bites. First, we substitute our values, replacing N with 4 and P with 0.3. We subtract 0.3 from 1, giving us 0.7, which is the 70% chance a single louse fails to infect. We raise this failure probability to the 4th power, resulting in 0.2401. Finally, we subtract this from 1. The final answer is 0.7599. Physically, this means there is roughly a 76% chance of contracting the disease from just 4 lice, highlighting the extreme danger of exposure. This mathematical reality we just calculated has profound implications for public health and medical safety. As we saw, even a minor exposure involving just 4 lice resulted in a dangerously high probability of infection. This perfectly demonstrates why medical personnel must wear strict personal protective equipment when handling patients with typhus or other louse-borne diseases. The math proves that you do not need a massive infestation to contract a deadly pathogen. A few vectors are more than enough. Therefore, controlling vector density through immediate hygiene interventions and laundering clothing is the absolute most critical step in preventing these localized outbreaks from turning into massive epidemics. As we conclude our lecture, let us review the most critical insights we have uncovered about the human louse. First, we learned that the body louse thrives in poor hygiene and relies on clothing to survive and multiply. Second, we discovered that it transmits deadly diseases like epidemic typhus through posterior station transmission, where infected feces are scratched into the skin. Finally, our mathematical models proved that louse populations grow exponentially, and the probability of infection rapidly approaches certainty as vector density increases. You now have a comprehensive understanding of both the biology and the mathematics behind this ancient disease vector. Excellent work today!